So the last half of chapter 16 is going to be about mountains building up processes and then some wearing down. And so mountains originate. We're going to talk about the origin of mountains. Mountains are elevated parts of Earth's crust, rising abruptly above the surrounding surface. So not like the rolling hills we have in East Texas, but we're talking about like the Rocky Mountains, the Appalachian Mountains, Cascade Mountains, big mountains, not rolling hills. They are created by the folding and faulting of the crust. So think back to those definitions we talked about in the last video. And there are three basic origins that we're going to cover: folding, faulting, and volcanic activity. So we're going to cover some different types of mountains. The first kind that we're going to talk about are the domed mountains. They have broad arching folds like you see here. They're overlying sedimentary rocks that will weather away, leaving more resistant granite peaks, which makes them a little bit harder material at the base because the softer sedimentary rocks have worn away. So you can see here they're kind of sloping domes, not very sharp peaks, and very kind of worn away, not very high angled, very low angled mountains. Now, fault block mountains are ones that are formed from our horsts and our grabens. And you can see here that they're going to rise sharply along steep inclined fault plains. And weathering will erode and reduce those sharp edges. And so you can see from the top image to the second image that the sedimentary rocks that will wear away kind of fill in and create different shapes. Volcanoes can produce volcanic mountains. It's when you have a hill or a mountain formed by the extrusion, so coming out of lava, or rock fragments from the magma below. Some of the structure features are the vent, the crater, the lava flow, and so you can see here on the bottom right, this is the Cascade, one of the Cascade Mountains. I think it's Mount St. Helens. So it's all by itself, not very sharp features, very tall, very sharp angles, very high incline, because this is taken up in an airplane. So that gives you perspective. If you're 10,000 feet up in the air and the mountains here, yes, it's still not as tall as the plane, but it's still fairly high. Now, mountains are built up by the folding and the faulting of volcanoes, but we also have this weathering process that's occurring, which is tearing down Earth's surface. So the definition of weathering is slow changes that result in the breakup, crumbling, and other destruction of solid rock. And we're going to have physical, chemical, and biological processes. These are going to contribute to the rock cycle, the formation of our soils, and the movement of rocks materials over Earth's surface. So how we get something from one place to another. Now, erosion is the process of physically removing weathered materials. So the movement. Something has been weathered down, either by water, wind, wherever. And erosion is the process of moving it from one place to another. So water may have worn the rock down, but unless the water moves the rock down the stream, it's only eroding if there's movement. Weathering is simply breaking apart. Eroding is movement. So they sound like the same thing, but we're talking about different things from the rock's perspective. Mechanical weathering is the physical breakup, so physically cracking apart rocks without changing the identity of the rock. So no chemical change, just a physical change. You can see here that it's a disintegration process. It can occur by wedging. So if you have a tree growing next to a sidewalk, eventually the root may cause the sidewalk to break, and that is a physical, mechanical weathering. Frost can also do it. So if you look in the bottom left-hand image, water seeps into the rock, and when it freezes, if it freezes there, the rock is then going to crack because the water will expand and basically cracks apart the rock. Now the image that you see on the right hand side it's kind of the middle image on the bottom where it looks like a dome shaped and there's pieces falling off, that's called exfoliation, and that's what's happening at Enchanted Rock. So you have pieces that are kind of coming off in a shell like an onion, exposing layers underneath. And then on the bottom right hand corner you have a tree that's growing in between a rock and it's kind of forced it apart, and that's an example of mechanical weathering. Now, chemical weathering is going to be decomposition of minerals by chemical reactions. The three kinds that we have are oxidation, carbonation, and hydration. So oxidation is what's produced. Our red soils here in East Texas, we have a lot of iron, reacts with oxygen, produces iron oxide, also known as rust. But on the right-hand image here, you see that red rusty kind of look. Well, that's oxidation. If you were to expose the rock underneath, it's probably not red like it is on the surface until it gets exposed to the air. Carbonation is what's happening with limestone. If you've ever seen an image where you have, let me see if I can find one. Like this. So these are all examples of limestone weathering away. Produces really pretty thing, but this is carbonation. Okay, it's what produces underground caverns. If you've ever gone to Lone Star Caverns in New Braunfels, you can see stalagmites, stalactites. Those are all produced as a result of a chemical weathering on limestone rock. And hydration is the process of a rock being dissolved by water. So this happens a lot to rocks that are nearby streams that are usually get year-round rain and stay full year-round. This would not be like your dry creek beds that are just like overflow or flash flood zones. All right, so running water is one of the most important gravitational erosional processes. So it's essentially what helps move sedimentary rock from one place to another. Okay, we've all been in or hopefully have all been in a stream where the ground is really silty, or the water's really silty, so you get in there, it's like real gritty, versus if you get into like a spring-fed creek, it's really clear and quite nice until maybe you step in it. So those are examples of rocks that they were eroded, weathered down at some point, and now they're being moved, being eroded somewhere else. So now stream beds will evolve over time. And so the way that it works is that when we have a youthful stream, we have a landmass that's recently uplifted. So up here in the right-hand image, kind of sharp mountains. You have a stream kind of running between the mountains. Very steep gradient, V-shaped valleys with no floodplain. So whenever there's a lot of rain, it's just going to flood very quickly downhill. You might have boulders, rapids, waterfalls, some features you might see. When you have a mature stream, normally the steep incline goes away and it's kind of more smooth, rolling features lower down. And there are meanders, which are kind of like streams, meanders over a floodplain. So they can still fill up and flood more than they did before, because those steep mountains that were like funneling the water down as rapids and rain and waterfalls are gone. When we have a stream that's very old in age, the surface around it's very flat, very low gradient, meaning not steep, broad, gently sloping valleys. The rivers are more slow, sluggish in their flow. So therefore, whenever there is a lot of rain, we tend to have floods. So the water will rise and it fills the floodplain area, and then it'll eventually seep back out. And so this is how a stream bed evolves over time. Now, hopefully you know that all water is going south. Water is not going up. So if you're in the Mississippi, the water is flowing down from north. Well, it starts all the way up higher than that, but North America all the way down until it gets down to, oh my gosh, New Orleans, Mississippi River. That's bad. Anyways, but down in New Orleans, it is below sea level, which is a problem in itself, but there is something called a delta. And out the delta, this is where you have a large amount of the sediment at the mouth of a river, which I think is the Mississippi River. I'm really blanking on that right now. And so because you have all of the sedimentary rock flowing down the Mississippi River from all over North America, it's going to be deposited somewhere. Well, in that case, it's going to deposit out at the mouth of the river, which is called the Delta. I'm going to look it up. Louisiana. Yeah, it is. Okay. The Mississippi River Delta is in New Orleans. Okay. So what this means, if we see this image right here, is you have kind of an area where there's a lot of silt deposits. The river, or the place where the freshwater and the saltwater mix, is going to be kind of high in nutrients but very diverse life. So what grows in a delta is not going to be the same as what's in a freshwater system or in a saltwater system. It's a little unique. The stream flow will dissipate into the ocean or the lake. So in this case, the Gulf of Mexico is where the Mississippi, that I do know, is where the Mississippi runs out. And there's going to be erosive and sediment carrying abilities lost because it doesn't have the flow of the mighty Mississippi anymore. So the rocks basically get thrown out of the Mississippi River and get deposited there like a dump truck dumping out its load at a job site. And then now it doesn't have anywhere to really go very quickly because the ocean is not a turbulent flow, or the lake is not a turbulent flow. But it makes for kind of a marshy condition, lots of life around the delta. And so that is and it's called the delta because of its shape. Okay, so I hope that helps you remember it. All right, glaciers is going to be the last thing we're going to talk about. So glaciers are where a small percentage of our fresh water is locked up. I think it's like 2%, 3% of all fresh water on Earth is locked up in glaciers. So that doesn't sound like a lot, but when you don't have a lot of fresh water to drink, sometimes those glaciers are looking pretty important. But unfortunately, they're locked up in there. We don't want to melt the glaciers. They are important. But glaciers are going to be huge masses of ice that are on land that move solely because they're so heavy. So if they're formed up at the top of a mountain, we're going to call those alpine glaciers. And they are going to move down the mountain. And they're like big pieces of ice that are just carving and scooping and making all kinds of, leaving all kinds of marks on the mountains around them. Now, glaciers come from snow that's been accumulated over many, many years, 3,500 years. So this is why it's so important, whether or not you believe global warming is real. We know that what we see in the glaciers tells us that we're going through a warming period. Whether or not that's global warming, at the level of which we're concerned, we won't really know because we've gone through many, many global warmings throughout our recorded history. And we know that because I think in the 1980s we had a small ice age. And I was alive in the 1980s and I don't even remember feeling like we were in an ice age. But the thing is that small temperature changes in the global temperature have a huge impact, even if we don't think they do. And one of those ways is the formation of glaciers. If the Earth continues to heat up and we don't have as much snow formation every year, what that means ultimately is we're not going to reform those glaciers as quickly as they're flowing down the mountain and melting. And what that means in the long term, we don't really know. We don't have a precedent to study to say, well, it happened here and this is what happened and we were fine. So that's kind of one of the concerning things because glaciers are important. Alpine glaciers that form at very high elevations, the top of mountains, they will flow down through the valley over the course of the year, so sometimes they're called valley glaciers. The other type of glacier that we have are called continental glaciers, and we have only two on Earth. They're called continental glaciers because they cover a very large continent. They are not formed up in mountains. They're very flat, planar type structure. And the two we have right now are Greenland, which is ironic because Greenland is icy and Iceland is green. And then, of course, the continent of Antarctica. And so, and if you've looked at anything about Antarctica, we know that the glaciers in Antarctica are falling off at a very alarming rate into the ocean, which is happening because of warming. There was a hole over in the ozone layer. I remember that being a big deal when I was in school. But we do know that the ozone layer is healing. What a wonderful world that God has created for us, that it will heal itself, that it can heal itself as long as we do the right thing by it. But it is the other continental glacier that we have on Earth. So this should end chapter 16. If you've missed something, please go back and listen. I tried to go a little bit slower this time, make a shorter video, talk a lot more like I would in class. But please let me know if I've missed something, you're confused about something. That's why I'm here. I'm still here to help, even though I'm not physically there with you. I couldn't be in all 11 places at one time, even if I wanted to. So please stay in touch. Look forward. Chapter 17 will be coming out soon.